Let's finish this paper. This is the last question. So let's break down this entire problem context into some straightforward mathematic expression. So first they tell you that it is equal mass. So you know that MA is going to be equals to MB. And they tell you that the specific heat of A is larger than specific of B. And then they tell you that the temperature change is the same for both A and B. And finally they tell you that there's no change of state. So they are asking you to explain which substance is having a greater change in internal energy, and the internal energy is basically your E. So, okay, what you can do is state which substance will have a greater change first, and then you explain. Always state the answer first, then explain. So, state it. The change in internal energy, okay, in A is larger. Okay, you have stated. Then explain. This is because E is equals to mc delta T. Since MA is equals to MB, delta T equals to delta B, and your C of A is larger than C of B, so hence your energy A will then be bigger than your energy in B. Okay, yes, you can use mathematic expression in your explanation. It is okay. Okay, let's look at part B. You are given a heating circuit, and you're saying that cold water as 14 degrees C is being heated up to 40 degrees C. You were given some information. This is going to be useful. So the heating element is given by this, and the specific heat of the water is given by this. So state how the thermal energy is transferred from the heating element to the water. So this is the heating element. This is the water pipe. This is the water pipe. Oh, so the heating element is inside the water pipe. Yeah. So state how it is transferred to the heating element. There's 2 marks, so you need to state 2 points. So basically, since the heating element is inside the water pipe, so imagine that this whole thing is a pipe. Okay, it looks like this. So it is a pipe. So because the heating element is inside the pipe, that means the heating element is in contact with the water, right? So because it is in contact, what is the mode of heat transfer? Conduction. So conduction will happen first. Then because now the liquid is being heated up by the heating element, it's going to expand, density is going to change, then you have your convection current start sinking in. Yeah, so you have 2 methods of heat transfer. So let's break it down. So the thermal energy is transferred to the immediate layer of water around the heating element by conduction. Okay, so first it is by conduction. When the subsequently, okay, so just use the word subsequently. Subsequently, the thermal energy is transferred to the rest of the water by convection. So the problem here is that some students do not know how to describe. So some of the keyword that I usually use when I describe this is like immediate layer, subsequently how the heat is transferred to the rest of the water. Okay, so it gives you a very short and precise answer. Okay, then for part 2, you have to estimate the flow rate of the water. Now, some students, when they look at this, they get very stressed out. Okay, do not get stressed out. Think about the situation here. What are some principles that you can use? Is it about pressure? No. Is it about force? No. Then it must be about energy. Is there heat in, heat out? Yes. What is the energy supply? Energy supply is by the heating element. Where does this energy goes? It goes into heating up the water, right? And there is this energy conservation going on here. So write it down. Okay, you will have the energy supplied by the heating element must be equals to the energy absorbed by the water. So far so good? Then you will be thinking, but teacher, it is not energy. What is given here is power. Then how? But remember this, power is also having an energy component, right? Because power equals to energy over time. So don't worry, break it down. Okay, I think I write off center, so I will shift it like to here. So this one will become power multiplied by the time, right? And down here you will get your MC delta theta, right? The energy absorbed by the water. Now then you ask yourself, but teacher, I won't have this kilogram per second. This is just kilogram. Now don't worry, okay? Let's find out how to get this. Now if we have something like that, you want to have per unit time, right? I only have kg here. So what I can do is that I can introduce the time component, but this is mathematics. So if you introduce time here, then you must also introduce time here. And you are introducing a term, right? A time term. You are not introducing a value. So this power times time, it is also a term, right? It is just a term. So this time and this time, they are both the same type of thing. Why am I saying that? If your flow rate is per second, isn't this energy per second as well? So if you are talking about the energy supply every 5 seconds, then your flow rate, the mass that you are calculating, is also every 5 seconds. Yeah, so therefore this time and this time is the same thing. You can cancel it off. So eventually your formula become P m over T. Because all these are multiplied together, you can play around like that. So now you have this term mass over time. Isn't it kg over seconds? So you have everything ready. So rearrange your formula, make this the subject. So you have P, bring everything to the other side. You have this. Okay, then substitute the value in. Power is given by 7.2 kilowatt. So remember it's kilo. Okay, then your this heat capacity is 4.2 times 10 to the power of 3. This is given by the question. Okay, and your change of temperature is from 40 degrees C to 14. Okay, now you have everything. Punch your calculator. Punch the value into your calculator. So let's do it. You will have this value 0.0659 round off to 3SF. So flow rate 0.0659 is kg per second. So not very hard, right? Okay, part 3. State 2 reasons why your answer to 2 is only an estimate. So you need 2 reasons. So look at this diagram. This is an electrical supply, right? there is some wire. Okay, heat transfer here, it is by conduction and all that. So conduction, convection takes time, right? So the heat transfer to the water that is flowing around it, does it happen instantaneously or it will take some time? It will take some time, right? And when the water has flowed past this heating element, it's going to lose heat, okay, through the pipe, right? And also if you have a wire here, the wire itself is also having some resistance, right? So will there be really 7.2 kilowatt? Will it be 240 volt? Because what you are saying here, this circuit, is that you have EMF, you have a singular electrical component, meaning that the 240 volt will be 100% used up here. But that is the ideal case, right? In theory, the wire itself is having some resistance as well. So this 240 volt, some of it will be spent on overcoming the resistance here. Okay, and the voltage and the energy here will be lost as heat to the surrounding. Then finally, the majority of the voltage will be spent here. So basically what you need to do is you need to acknowledge that this is not equal. Okay, some of the energy supplied by the heating element is going to be lost to the surrounding. Okay, not 100% is going to be absorbed here. So state the two reasons. Okay, think about it. Then you state. So first, okay, energy lost. Okay, when current flows through the wire in the heating element circuit. Okay, first stop. Basically, if you for the sake of this walkthrough, the energy loss, right, is going to be equals to I squared R. Okay, where R is the wire resistance. Okay, yeah, and you can then calculate this rate of energy loss. Okay, you can calculate it out. Okay, then the second reason, okay, is that the heat transfer does not occur instantaneously. Okay, the heat transfer, don't forget, is between what? Between the heating element and the water. Okay, because the water is flowing, the water is not stagnant. Okay, so if the flow rate is too fast, okay, you may not even capture that much of energy from the heating element. Now the third reason is that some heat is going to be lost to the surrounding. Okay, from the water. Okay, so not 100% of the heat. Energy conservation is true, but it is very hard to conserve it in an open system when you have the surrounding there. Okay, it is almost impossible to avoid.